In this lecture video, we will introduce a new quantity or concept called electric potential. An electric potential is simply the electric potential energy per unit charge. What we saw in the last lecture was that if a point charge Q moves around in vicinity of another charge, there is a potential energy change, delta U, okay, which depended on both the magnitude and sign of Q. So what we can do is we can simplify the conversation. Instead of talking about the energy between the two charges, we can talk about the energy per unit charge. We call that the electric potential. So the electric potential V is simply equal to the energy between the two charges divided by one of those two charges, which we call the test charge, which is sometimes written as Q naught. And so that's the equation we have right here. So the electric potential is related to the electric potential energy. We denote the electric potential by the letter V, and that's equal to the electric potential energy for a charge Q naught at a position divided by the charge itself. So we divide out by the Q naught, which we call the test charge. And we assume that that charge has a small magnitude, so it doesn't affect the other charges that create the electric field that it moves in. Because we divide out Q naught, the value of the potential at any given position, it doesn't depend on Q naught at all, right? Instead, it depends on the other charges that are producing the electric field at the position where we place the test charge. Much in the same way as force being an expression of an electric field, right? What we saw in the last chapter was the electric field was the force per charge, right? The electric field allowed us to talk about the force between two charges, but we can neglect one of the charges. So the electric field tells us the force that would be between two charges if a charge was at that location. And what we remember is that the force, right, was equal to, let's do the big Q, little q, right, Q naught test charge over R squared. And the way we described the electric field was, well, it's the force experienced by Q naught if Q naught was there, right? So it's force divided by Q naught. And we recall that the equation for the electric field would be KQ over R squared, where big Q is the charge responsible for creating the field. And the test charge is there to feel the field. So the relationship between potential energy and electric potential is exactly the same. So the potential energy between two charges, let's use red and blue, okay, separated by a distance r, was equal to K, little q, big Q over R. Well, the potential that exists is the potential that big Q creates for any charge, such as little q, to experience. And this is a V, by the way. So for the electric potential energy, the value of U electric for a charge at any position, it's not really as important as the potential difference. So when we talk about potential, we talk about energy, we're usually always going to be referring to the delta U or the delta V, the difference in the potential at any point, okay? So there are situations where we will be calculating V or calculating U, but in most of the questions, we're going to be concerned with the change in V or the change in U. Okay, which is the difference in potential or the difference in potential energy between two different points in space. And so we can define then potential difference as being the potential energy divided by Q naught. Or I should say the change in potential energy divided by Q naught. So what are the units of potential or potential difference? The unit is also given by the letter V, and it's called the volt. Okay, so the units of potential and potential difference, V or delta V, is the volt, V. So there's a lot of V's going around. And you are probably familiar with this quantity, volts. You've seen it before. Batteries are defined by how many volts they have. So a AA or a AAA would have 1.5 volts typically. And what does that mean? Now you are starting to learn what that means. So that means that the electric potential at the positive terminal of the battery is 1.5 volts greater than the electric potential at the negative terminal. So this value, 1.5 volts, is actually delta V. So, right, it's the electric potential difference, delta V. And let's talk about what that means. So what does that mean that there is a potential difference? Well, if we take a look at the units of volts, the units of volts is equal to 1 joule per coulomb. Okay, and so joule is a unit of energy, coulomb is charge, right? And that's because we remember that V volt is energy over charge, right? So that would be units of joules over coulombs. So thinking about that, joules per coulomb. This means that if the electric potential at some point B is 1 volt higher than point A, then to move a charge of 1 coulomb, it would take 1 joule of work to do that. Okay, so potential difference is a joule per coulomb. It means it takes 1 joule of work to move a 1 coulomb charge through that potential difference. And so the beauty of referring to potential difference versus energy is that we can talk about any arbitrary charge. So what if that charge instead was 2 coulombs? Okay, well, the energy required to move it from A to B would mean you would need 2 joules of work to do that, because 2 joules over 2 coulombs gives you 1 volt, right? So that allows you to use this quantity of 1 volt to talk about any particular charge, not just 1 coulomb, but 0.5 coulombs, 0.7 coulombs, okay? So a 0.7 coulomb charged particle, it would require 0.7 joules of work to move it through a potential difference of 1 volt. So 1 volt can also be expressed in SI units as a Newton meters per coulomb. Why? Because a joule is defined as a Newton meter. So if we think about that unit, okay, then we can express a voltmeter as a Newton coulomb, which is, you might recall, this is the units of an electric field. So we can actually express an electric field now. Instead of a force over charge, we can express it as a potential over distance. It's an equally good set of units for electric field. And as we get more comfortable with potential difference, this is going to make a lot of sense, expressing electric field as a volt per meter instead of a Newton per coulomb. So another idea is that, not an idea, a convention. Another convention, and you'll hear me say it a lot, is we'll often shorten the word electric potential and electric potential difference. We'll just refer to it simply as potential or potential difference. So another way to name these quantities is sometimes we will just refer the potential difference as a voltage. So when you're first getting comfortable with this terminology, it can get a little confusing because we use the symbol V to denote electric potential, and we also use the letter V to represent the units of volts. So typically, you will see a quantity V, which represents electric potential or voltage with an italicized script, okay? And then the units are never italicized. So another thing you must watch out for is, well, although they sound similar, electric potential and electric potential energy, they're not the same thing, right? Electric potential energy has units of joules, and electric potential has units of joules per coulomb, or Newton meters over coulomb. Let's take a look at an example that helps us get kind of used to this terminology. So let's place an electric field pointing down, and let's take a look at what the electric potential difference would be between 2 points in this electric field. So you may be wondering, like, okay, I have an electric field here and I have like points in space A, B. Where are these charges at, right? I thought we were dividing by charges and that, U is equal to KQQ over where are the charges at? So remember that an electric field exists because a charge exists, right? So if we have an electric field pointing down, that could be created a couple of different ways, but they're all equivalent. That could be created by a particle down here that is negatively charged, right? Because we know that electric fields point towards negative charges. That electric field could be created by a positive charge up here because we know that electric fields point away from positive charges, or that electric field could be created by both a positive and a negative charge separated by some distance, okay? So there are charges here, but we don't talk about them because when we look at the electric field, we know that they are created by charges. And so what about the second test charge? Well, the test charge, Q naught, that's going to be who we place at A and B and do our calculations, okay? So A and B are the locations where a charge could potentially be a test charge that's going to interact with that electric field. So let's remind ourselves that the change in potential energy when a charge Q naught is moved in an electric field is minus QED cosine theta. And where did that come from? Remember, we defined work done as FD cosine theta, and that force is equal to QE, and then we plug that in, QED cosine theta, and then we said, oh, wait a minute, remember that work is equal to negative delta U, so we throw a negative sign in front of QED cosine theta. So that's just a little reminder. Where did that statement come from? That's where it came from, so recall. And so what this equation tells us is that the electric potential difference between A and B is going to be simply this equation here divided by Q. So the Q would drop off. And therefore, our delta V is going to be negative ED cosine theta. Okay. So the potential difference, delta V, is going to be positive if cosine theta is negative. Why? Because remember, we always leave these as magnitudes. And let our cosine theta give us the negative or the positive. Okay? So under the same reasoning, delta V will be negative if cosine theta is positive. In other words, in a phrase or in a concept, if you move in a direction opposite to the E field, the potential increases. If you move a charge in the direction of the electric field, the potential decreases. And you can think of that by remembering what is creating that electric field pointing down, or in your problem, whatever direction that electric field is pointing. You can picture a charge creating that. And it's probably best to picture it both as a negative and a positive charge creating that electric field. And so if we want to keep delta V sign the same, we should let our Q naught be positive, right? Or else we'd be flipping the sign. So let's imagine a positive charge Q naught going from A to B up here. Well, if this charge's Q naught is positive and it's moving closer to another positive charge, well, it's moving in the opposite direction of the electric field, and you're increasing its electric potential, right? Because then when you are bringing it closer and closer to this positive charge and you let it go, it's going to have a lot of energy to fly away, right? Because you're bringing it closer to another positive charge. It doesn't want to be there. It wants to buzz off and fly away on its own. So you're increasing the electric potential there. Now, instead, if you take that positive charge, okay, let's say Q naught is positive, and you're moving it closer and closer to a negative charge, which would be down the electric field, okay, in the same direction as the electric field, well, then you're decreasing the potential. Because if you were to let it go, it would just go straight towards this negative charge. So that is just, using the idea in the previous lecture where we can express the electric potential energy as how much work you would have to do to bring the charge from infinity to that current position. That's the concept we're using to explain the potential increase and decrease, okay? So we know that the electric force on a positive charge is in the direction of the E field, and the electric force on the negative charge is opposite the E field, right? So our observations about how electric potential charges changes with position, is basically similar to what I just explained up here. For example, if an object has positive charge, well, then the electric force on that object pushes it towards a region of lower electric potential, right? Because a region of lower electric potential is near a negative charge. So if we have a positive charge here and we let it do whatever it wants, it's going to want to go down. It's going to want to go down closer to a negative charge, right? Because it has an attractive force there. If an object has a negative charge, well, the electric force is going to push it towards the region of higher potential, right? Higher potential is closer to a positive charge. So if we have a negatively charged particle and we let it do whatever it wants, it's going to want to go this way, right? Towards a positively charged particle. Because this is negative and this guy positive. So this is always true whether or not the electric field is perfectly uniform. And what does uniform mean? Uniform means that that the electric field has the same value everywhere in space. That's what uniform means. Okay, so like in this picture, The E field right here is 10, the E field right here is 10, the E field right here is 10, the E field right here is 10. That's what uniform means. So another way to think about the potential difference between 2 points, and this is what we talked about in the previous lecture, is we can think of it as negative of the work done by the electric field. Why? Because remember in that italicized bullet point in the previous slide, we said that we can think of potential energy as the work that you and I would have to do to move the charge, right? And we know that external work is equal to negative of the work done by the field, by the electric field. Okay, so this is the same way of thinking about it as we talked about in the first lecture slide where we introduced electric potential energy. We can use that same method when we talk about electric potential, and that is we can think about it as negative of the work done by the electric field, which means it's the work that you and I or an external force would have to do to overcome what the electric field wants the charge to do. So, in other words, in terms of potential difference, the potential difference between 2 points equals the work that you must do per unit charge against the electric force to move a charged object between those points. So, for example, if you take a charge, 1 Coulomb charge, positive, and you move it from point A to point B, and the potential at point B is 1 volt higher, then the electric field does negative 1 joule of work, and you have done positive 1 joule of work on that charge. Okay, so let's kind of draw this idea out. So you have point A and B, and you take this positive charge, and you move it from A to B, and the result, or what you know about that area is that the potential difference between A and B is plus 1 volt. Well, that statement can mean 2 things, and they're both equivalent. It means that the electric field has done negative 1 joule of work to move that charge, or that we have done positive 1 joule of work to move that charge. Okay, they're equivalent statements because the negative sign there, right? Because work done by the field is negative of external work and vice versa. They're related by a negative sign. So let's do this example where we calculate the potential difference between 2 points to really illustrate what this delta VAB means, right? The potential difference between point A and point B. So we have a uniform electric field and it's pointing in the positive X direction. And its magnitude is 2. And if this seems familiar, it is, because we are kind of doing the same problem again, but we're analyzing it from a different point of view, from the view of electric potential. So points A and B are both in the electric field. Point B is a distance 0.3 meters from A in the negative X direction. Okay? B is over here, A is over here, right? Because the negative X direction is to the left. Determine the electric potential difference, VB minus VA, between those 2 points. So let's use this definition of potential difference up here. V is negative ED cosine theta. Okay, let's use this. V is negative ED cosine theta. Delta V. And so let's fill in the blanks, okay? Well, magnitude goes here, magnitude goes here. So delta V is going to be negative 2 times 10 to the 2. And then the distance traveled was 0.3 meters. And so now we need to figure out what theta is going to be for that move. Okay, the move from A to B. So theta is the angle between the E vector and the D vector. Okay, so the E vector is pointing to the right, and the D vector, or the displacement vector, well, that's going from A to B, which is moving to the left. So the angle between those two vectors is going to be 180 degrees. Okay, and so then we're going to get a negative from this. It's going to cancel out the negative in the front, and we're simply going to get 2 times 10 to the 2 multiplied by 0.3 meters. Okay, which gives us 6 volts, positive 6 volts. So the negative sign that is attached to the definition of delta V, that got canceled with the fact that theta was 180. That is the angle between the electric field and the displacement is 180, which is -1, and those canceled. Okay, so we got 6 volts. So here's a schematic of that, right? So A to B was in the negative X, E is in the positive X, so the angle is 180, and then we just simply plug in the values. So, you know, math-wise, not terrible, okay? Concept-wise, a little fuzzy. Like if you wanted to have a short conversation with somebody about an electric field and moving a charge to the left in that electric field, that would be a little fuzzy. And so getting comfortable with the terminology and what it means is going to take time and reading, and a lot of reading. So reading the slides, doing the examples, talking to other students, talking to me, okay, that's going to help you get comfortable with the terminology. So, and reading all these slides that go with the example is really going to help you too. But I don't have time to read, you know, with you. Let's do one more example. Very similar to the previous one. So let's figure out what the electric potential difference is between a point in an electric field and another point that is 0.5 meter from point A, and this path taken is a straight line that makes an angle of 126.9 degrees with respect to the electric field. So we have the same electric field as in the previous example, right? Points to the right. Point A is somewhere in that electric field. And now we have point C, which happens to be 126 degrees with respect to the electric field. So 126 degrees, well, 126.9, we can actually, because it doesn't tell you which way to rotate, right? So technically, this is 126.9 degrees. This is also 126.9 degrees. So it's not clear which path is taken. Okay, if this is point A and this is, we don't know if it's this point C or this point C, but that's okay. We're going to do both and you're going to see something. Okay. So we're going to set it up in the same way we did in the previous example. So we know that delta V is negative ED cosine theta. And the E and the D are going to be positive values because these are magnitudes. And if there is a negative sign involved, it's going to come from the cosine theta. Okay? So positive or negative, and this is always positive. So let's calculate delta V. So we have our minus sign that is part of the definition. E is the same value it was in the previous example, 2 times 10 to the 3. D is now 0.5 meters. And then the angle between E and D, it was given to us pretty directly, but it wasn't clear if it was rotating up or rotating down. But if either way, it's 126.9 degrees. And you can see that there really is no other way to write that. I mean, there is, right? You could put in cosine of negative 126.9 degrees. Typically, that's how we refer to a rotation that is clockwise from an x-axis, okay? But if you know or remember anything about cosine functions, is cosine of x equals cosine of negative x, right? Cosines absorb their negatives. Sines, just as a little aside, right? Sines, sine of negative x is actually equal to negative sine x. So sines pull their negatives out into the front. Cosines absorb their negatives, okay? So what you're going to see is that regardless if you put in 126.9 or negative 126.9, you're going to get the same answer. So what is that answer? Let's get the calculator. Okay, so I get a positive 600 volts. And you can convince yourself by going ahead and typing in a negative cosine of negative 126.9, and you can see that you get the exact same value, which is negative 0.6, right? Both of these, equals negative 0.6. So our potential difference is 600 volts, positive. So let's take a look at the example. So it looks like the book decided to define this as 126.9, but I think I have convinced you now that either way you decide to put C, as long as this angle is 126.9, you have an area of equal potential. And we're going to talk about equal potential in the next section. Okay, so just keep that in mind. I believe there's one more. Yes, there's one more example after this. This example I'm not going to include in this lecture. I'm going to have it posted in the PCAST section of modules chapter 17. Okay, so this lecture is already getting a little bit long. So this example is pretty quick. I know it looks long, but it's mainly a word problem, and there's really only one little piece of information that you need. Well, one here, and you need to know what it's wanting, and also that they are initially at rest, right? So there's the main pieces of information that you need for that example. So I want to kind of give you another form or another unit for potential energy change. Okay, so we're switching gears. We're talking about energy again, right? We're talking about U. And remember that U is equal to, well, let's remember that V is equal to U over Q. And in a previous problem, I rearranged that as U being equal to QV, right? So take a look at this. If potential energy is equal to charge times voltage, I can express a unit of energy as a charge times a voltage, right? A QV or a CV. And it's very common for scientists and, anyone working with high energy, radiologists, to express energy in terms of this unit called an electron volt. Okay? And so an electron volt is equal to an energy. It's an energy that is equal to the magnitude of the charge of an electron times 1 volt. And since we know the charge of an electron is 1.6 times 10 to the minus 19 coulombs, the energy value of 1 eV is 1.6 times 10 to the minus 19 joules. So how did that turn into joules? Because a coulomb times a volt gives you a joule. And we see that right here, right? This is units of coulomb, this is units of volts. So a coulomb times a volt must give you a unit of energy, which we know very well as being a joule. So an electron volt is just another way to express energy. And that's because if we were to leave, if we're talking about particles like electrons, protons that have very small charges, right? The magnitude of the charge is on the order of 10 to the minus 19. And we're accelerating them on potential differences, even up to 100,000, right? Or more. We're still going to get a very small number, right? If I multiply 10 to the minus 19 times 100,000, 1, 2, 3, 4, 5, right? I had to remind myself what 100,000 is. It's 10 to the 5. We still get a really small number. And, when you talk about numbers so small, they can kind of seem insignificant or confusing or meaningless, right? And so, therefore, it makes sense to instead convert that energy of 10 to the minus 14 joules into EVs. Okay, and the conversion factor is simply 1 EV equals 1 times 1.6, or 1.602 times 10 to the minus 19 coulombs. Okay, so if I want to convert this coulombs, joules. If I want to convert 10 to the minus 14 joules into EV, I just multiply it by the conversion factor, and I get 10 to the minus 14 divided by 1.602. Just plugging in my calculator right now. I get a much more manageable number, about 62,000 volts or EVs, right? So it's just a number that has a little bit more meaning to it because it's not some kind of like crazy small number. And the other fact is that that this number is related to an electron, okay, or a particle with the charge of an electron. And so that's what this text is basically explaining. So I've talked to you a lot about electric potential. We did some math, and now is time to look at some pictures. And as usual, we're going to use a point charge as our study. Okay, so let's examine the electric potential due to a point charge. So we know the equation of electric potential energy. It's K QQ over R, right? As we learned in the beginning of chapter 17. So in order to find the potential, all we need to do is divide by the test charge. And when we do that, we divide by little q and we end up with K big Q over R, right? Where Q is the value of the point charge that is producing the electric field. R is the distance from wherever we want to know the information about to that point charge Q in the same way as we defined an electric field, and V is obviously going to be the electric potential. Okay, so what you may notice about this is that the potential around a point charge is going to be constant at a particular radius, okay? So the other thing you're going to notice is that the potential is going to be positive for positive charges and negative for negative charges. So let's kind of draw a little picture here. So if I have my positive charge, I have my negative charge, and if I draw circles, let's draw just a couple of circles around here. Why am I drawing a circle? It's not the greatest circle, but imagine, okay, let's redo it. Okay, imagine these circles being perfectly centered on the charges, okay? So if I am a distance of, let's say, R1 away from this charge, and this is R2, well, the value of the potential anywhere on this circle will be given by KQ over R1. The potential anywhere on this circle will be given by KQ over R2, where Q is a positive charge, okay? So the closer you get to the charge, the higher the potential. The farther away you get from the charge, the lower the potential. But anywhere you are around a positive charge, the value will be positive. And I'll just write that here. And it's larger because it's closer to the charge, so R is small, making V big. Here, R is a little bit bigger, making V smaller. And so we can kind of analyze these circles around, and those circles have a name, and we'll get to the name. We can analyze these circles around a negative charge in the same way. So if this is R1, okay, anywhere on this circle of radius R1, we're going to have a potential equal to K, and then Q is negative now, right, over R1. And here, anywhere on this circle, we'll have a potential of K with a negative Q over R2. And so all of these will be negative. This one will be larger because we're closer to the negative charge. And then these are all negative, but smaller value of V because R2 is bigger than R1. Okay, so now we can kind of like see a picture of what's going on, and that will maybe help you make sense of this new unit of potential, okay? So, and then these charts kind of explain exactly what I just did here, but I did it in terms of circles around the charges. These graphs explain the same thing, right? If this is the distance from the charge and this is the value of the potential, well, the closer you are, right, the smaller the R, the larger the V. The smaller the V, the larger the R. I'm sorry. The smaller the R. Okay, I got it wrong. So the larger the R, the smaller the V. There we go. And all those values are positive, because anywhere around a positive point charge, you'll have a positive potential. Now for a negative charge, right, the smaller the R, the larger the V, but that V is negative. The larger the R, the closer V gets to 0, right? It becomes small magnitude, but it is negative. So, let's take a look at the equations for electric potential and electric field, right? They look very similar, but the difference is what's in the denominator, right? The denominator in potential is R, but the denominator in electric field is R squared. So they both have that inverse proportionality, right? The really strong electric fields are close to the charge producing the field. And the really strong potential or the really high potential values are located at radii very small and very close to Q. So we can determine the electric potential due to more than one point charge in the same way that we can determine the total energy of a group of point charges. All we need to do is add the potentials together, okay? And making sure to include the sign of the charge and the proper distance that we are from this charge, right? So the distance that the point is from this charge and the distance that the point is from this charge.